Good evening, everybody, and welcome to Methods TASC4, specifically for the Tasmanian mathematics curriculum. This evening, we're hoping to get through a few questions focusing on function study, trigonometry, and differential calculus. So hopefully you have already downloaded the question sheet that I'm going to go through, so you may be familiar with the questions. And the idea is to learn to use your graphics calculator efficiently, effectively during an exam style question to maximise your marks at the end of the day. So let's commence. Question 1. Determine the equation of the cubic function drawn below. Give your answer in factored form and in expanded form. So I've got two things to do there. Now, there's not a lot to do on the graphics calculator for this one because you first of all need to come up with the factorized expression. And if you have a look at that graph, you have got a double solution at x equals -1, and you've got a single solution at x equals 2, and we know that the function is passing through 0,4. So the first thing we can do is write down a factorized expression. So y is equal to, we have a dilation factor, we then have x plus 1, and we're going to square it because it is a double solution. The curve is touching or bouncing off the x-axis at -1. And we then have a single solution at +2. So we've got x minus 2. There's our factorized expression. The only thing we need to do now is figure out what this dilation factor is at the beginning there. And to do that, we use the y-intercept, which is 0,4. So we're now going to substitute in 0,4 in order to figure out the dilation factor. And so doing that, we've got 4, which is your y value, is equal to a. X is 0, so we've then got 1 squared, which is just 1. And we've got 0 minus 2, which is -2. Got a little linear equation there to solve, and almost by inspection, you can say that your dilation factor is -2. That then gives you your factorized expression for that cubic. So we've got y equals -2, x plus 1 squared, x take 2. Now, the second part of that question is to answer in expanded form, and this is where you can use your calculator. It doesn't take you long to do that by hand. So let's just have a quick look on the calculator. I'm going to graph that first of all. So if I add in a graphs page, we have -2 multiplied by, it was x plus 1 squared, multiplied by x take 2. And if I graph that, there is my cubic that we've just come up with. And if I now want to expand that expression, I note that it's function 1. So in my calculator page here, I can type in the word expand, or if that takes too long, you can go menu, algebra, expand and access it that way. And I'm going to expand function 1, and the variable is x, and there is my cubic in expanded form also. So that is your cubic question 1. Moving on to question 2. We have got a parabola that's been drawn for you. They've given you the parabola. We've got to transform that parabola into a new function, g of x, by reflecting it in the x and y axes. So we've got two transformations to do, two reflections. Sketch the resulting graph on the same axes. Now, the calculator is very useful for this one. So first of all, let's get that parabola into the calculator. I'm just going to always close my pages that I've been working on and open up fresh pages. now got a graphs page, and I'm graphing 2 multiplied by x take 1 squared, and then I've shifted it up 2 spots. There is my original parabola that's been given to you in the question. Now, you can also bring up the grid to make things a little bit more visual as well. So if you hit Menu, View, which is number 2, and you want to view the grid, which is number 6, and we want to view the lined grid. And it just puts a nice grid on there just for some reference points, which makes life a little bit easier. Now, again in the question, it's asking us to reflect it in the X and Y axes. So what we can do is we can enter a second function, and we're going to do a reflection. We're going to first of all reflect in the X axis, so we're going to flip that parabola upside down, and to do that we just make the original function negative. So if we type in negative function 1 of X, I am reflecting my original function in the X-axis, and there is my first reflection. I then want to reflect that again in the Y-axis. So I'm now up to function 3, and remember to reflect in the Y-axis, we put a negative in front of the X value. We're switching the X values around. So I'm going to get function 2, which I just graphed, and I'm going to switch the X values around. By putting a negative in front of the X, I'm reflecting in the Y-axis. And when I do that, there is my reflected function. And that function there, you would now draw onto your exam paper in the correct position. Sketch the resulting graph on the same axes. You literally copy that new black graph onto your question paper. Second part of that question is to state the equation for your transformed function. So state the equation for g of x, and note that it also says no working is required. Again, you can just use your graphics calculator to write down the answer. So back on the calculator, we need to find out what that new function is. And if I open up a calculator page, remember that my original function was f1. So if I bring up f1, that's my original function. And I'll just hit enter so you can see there it is there in expanded form. Now I can do what we just did in the previous screens, put in the negatives. So if I go negative function 1, evaluated at negative x, because I've got 2 reflections there, hit enter, there is my new parabola. That's my gx function. And what I can do now is put that into turning point form also to make it a bit more user-friendly. So if I use the completing the square function, menu, algebra, completing the square, and if I go up and grab that function, paste it in there, comma x, because you've got to tell the calculator what the variable is, it completes the square for me. And so there's my gx function, negative 2, x plus 1 squared minus 2. And just to double check, we can actually graph that function back on our other graph. So minus 2, x plus 1 squared take 2. If I graph that, minus 2 multiplied by x plus 1 squared take 2. There it is, sitting on top of that black function that we drew before. All matches up nicely. So we've done part B as well too. So there's that question done. All right, question 3. Now this is another exam question, not much to do on the graphics calculator other than learn how to use the log function really. So what you've got there is the equation for the magnitude of an earthquake, the Richter scale. M equals log base 10 of I over S. I is the intensity, and S is the intensity of the smallest or standard wave. An earthquake that registered 6.4 was followed by another one which was 4 times more intense. Determine the magnitude of the second earthquake to 1 decimal place. So what's happening here is we've basically got log base 10 of I over S. That is currently 6.4. That is our current earthquake. We now have a new earthquake that is 4 times more intense. So what's going to happen now is our intensity is going to increase by a factor of 4. So we now have log base 10 of 4I over S. Our intensity has gone up by a factor of 4. And now using your log laws, you can separate that log function out into log base 10 of 4 plus log base 10 of I over S. And so what you've done is you've used your log law that when you're adding logs with the same base, you're multiplying them. And now here's where you can use your calculator. We need to work out what log 10(4) is. We know what log 10I over S is. That's our 6.4. We've been given that. So on your calculator, log 10(4). All right, back on my calculator page. So control log base 10 of 4. I get 0.6. So back here, I now need to add on. So I'm now going to add on my extra 6.4. So I'm now adding on my extra 6.4. 7.0. And so what is the magnitude of the second earthquake? It is 7.0 to 1 decimal place. So once again, not a lot of graphics calculator work there, but useful for logs. Okay, that's question 3. Question 4. What we've got here are some functions. We've got Celsius, and they're using the letter T to represent Celsius. Fahrenheit, F, and Kelvin, K, are 3 different temperature scales. And they're giving you the functions there. So this first function, TK, is for Celsius in terms of Kelvin. You've got the Celsius function in terms of Kelvin. Then the second function is the Fahrenheit scale in terms of Celsius. T is your Celsius. So you've got 2 different equations there. Determine a composite function to convert Kelvin into Fahrenheit. So what we essentially need to do is we need to substitute the first function into the second one, because that will give us Fahrenheit in terms of Kelvin. And we can do all of this on the calculator. The first thing we need to do, I'll just close these other pages. The first thing we need to do is enter those 2 functions, and I'm literally going to type them in as you see them. So we've got TK, so T bracket K. Now, instead of pressing equals, we're going to go defined to be equals. So control, and then in blue, close to the number 9, you've got a colon and an equals. That is the defined function. So TK is defined to be equal to, and our formula was K takes 73. So K minus 273, and locks it in. We're going to do exactly the same for your Fahrenheit formula, F of T. So F evaluated at T, defined to be equal to, and it is 9/5 T plus 32. So 9 over 5 multiplied by T plus 32. And again, that is locked in. And as we said, what we need to do is substitute the first Celsius formula into the second one. On the calculator, it's just a matter of going function f, and we're going to substitute in tk, so t evaluated at k. And there is our result. So that is the formula for Fahrenheit in terms of Kelvin. 9/5 K take 2297 over 5. All right. Second part of the question, part B. Hence, so that always means using what you've just done. The word hence means use what you've just done to convert 293 Kelvin into Fahrenheit. So back on the calculator, we now need to substitute 293 into our expression there. And what I'm going to do is I'm going to save that expression as FK. So I'm going to use the store function. So control, and then just above the var key here, you can see a store. It's going to store my answer, and I'm going to call it Fahrenheit evaluated at K. And it stores that function. And now that function is stored in the calculator, and I can substitute in the number that we wanted, which was 293 Kelvin. And it's going to convert the Kelvin into Fahrenheit for me, and I get 68 degrees Fahrenheit. So the answer there, 293 Kelvin is 68 degrees Fahrenheit. Part C, set up and solve a linear equation to determine the temperature that is the same on both the Celsius and the Fahrenheit scales. So we're going to find the temperature that's the same on both of those scales. Now, have a look at your second equation that you've got here. That equation is the relationship between Fahrenheit and Celsius. We want them to be equal to each other. So basically what we need to solve is we need to solve Fahrenheit equals 9/5 times Fahrenheit plus 32, because we want the temperatures to be the same. Alternatively, you could have said Celsius equals 9/5 Celsius add 32. It doesn't matter which one you're going to use, you're going to get the same result. Once again, you can use the solve command on your calculator. So we're going to solve, and it was C equals 9/5 multiplied by C, add 32, and we're solving for C. We get negative 40. So that's negative 40 Celsius. It's the same as negative 40 Fahrenheit. And so the temperature that is the same is negative 40 degrees Celsius or negative 40 degrees Fahrenheit. That is the same on both scales. All right, question 5. We've got a trig function, and we're asked to state the coordinates of all maxima, and we've got a domain there from minus 8 pi to plus 8 pi. So let's have a look at the graph first of all and see visually what we're talking about. So we're going to graph that. Just going to close that page and open up a new graphs page. Now, one important thing to remember is to make sure that you are in radian mode. Top of your calculator there, please make sure you're in radian mode. Sometimes calculators, if you've reset them, might go back to degree mode, but given that you're doing a Methods 4 course, we definitely want to be in radian mode. Otherwise, things might go terribly wrong for you. All right, now we are graphing 3 times sine x over 4. So we've got 3 multiplied by sine of x on 4. Now we can put the domain in if we want, so let's put the domain in. So we're going to use the conditional command, and to access that on the calculator, if you hit the control key and then equals, you'll see that vertical line. It's a bit like the vertical line that you see in conditional probability. It's a given command and it's a condition. So let's put that vertical line in, and our domain was minus 8 pi less than equal to x less than equal to 8 pi. So I've got our domain in there. And that will only graph the part of the curve that we're interested in. So I'll just need to change my window settings. So window zoom, window settings. Now remember, I want to go from minus 8 pi, so I'm just going to go to minus 9 pi, just a little bit past it. Then I'm going to go up to 9 pi, and I will leave the y values as default. Okay. And you can see my sine function graph there between minus 8 pi and plus 8 pi. Now the question is saying, state the coordinates of all maxima. Looking at the graph, we are trying to find the coordinates of those two maximum turning points. Very quickly on the calculator, menu, analyze graph, maximum. Slightly to the left we click, slightly to the right, there's our first maximum turning point. And the other one, analyze graph, maximum, slightly to the left, slightly to the right. Now, if you think carefully about it, 6.28 looks to me like it's 2 pi. Pi is 3.14. If we double it, we get 6.28. So that's 2 pi. And have a look at minus 18.85. That looks to me like it's going to be about 6 pi. 6 3s are 18. That's about minus 6 pi. But we can confirm that doing some calculus. So if I open up a calculator page, now to find maximum turning points, we want the derivative to be 0. So let's do the derivative. So I want the derivative with respect to x, and my function was 3 multiplied by the sine of x over 4. There is my derivative. Now I want that derivative to be equal to 0, so I'm going to set up a solve. So I'm going to solve my derivative. I can just go up and grab it. And I want it to be equal to 0, and I need to solve for x. I have to put in a domain. If I do not put in a domain, I'm going to get general solutions. I'll show you what happens. If I don't put in a domain, I get that funny looking expression there. Now, if you haven't done general solutions before, it's going to look a bit odd. So let's put in a domain. So I've got to use the conditional command again. So control equals, I'm going to go and grab my given, and I'm solving it over the domain minus 8 pi less than equal to x less than equal to positive 8 pi. And now I get my 4 solutions. And if you have a look at those 4 solutions, they will correspond to the 4 turning points, including the minimum turning points also. So to answer our question here, it says state the coordinates of the maxima. Our first maxima is going to be at minus 6 pi, 3, and our second one is going to be at 2 pi, 3. And that matches up with the minus 6 pi and the 2 pi that we've got as our solutions there. All right, that's question 5. Question 6. Determine the number of solutions for sine theta equals negative 0.7 over that domain and provide reasons. All right, that's a very big domain. We're going from 0 to 51, and we've got a sine graph. So let's graph that on the calculator. So I'm just going to delete these pages again. I'm going to put in a new graph, and I'm going to graph sine of x. All right, I'm graphing sine of x, which is the same as sine of theta. There's my sine x graph. Now, the second part of the question is I need to make that equal to negative 0.7. So I can add in a new line. So if I hit tab, I'm going to put in negative 0.7. It puts my horizontal line. And if we now change our domain, so if I hit Tab and go back up to the graph that I entered previously, my domain had to go from 0 to 51 pi. So I'm going to put in that given command again. So given, I'm going from 0 less than equal to x less than equal to 51 pi. And I'm just going to do a zoom fit now so that it will fit to the screen. Menu, window zoom, zoom fit. Still hasn't fit to the screen, so I'm going to go menu, window zoom, window settings. I'm going to go out to 52 pi, just so I can go one past. And there is my messy looking trig graph with my minus 0.7. Now you can sit there and count up all those numbers, or you can kind of think a little bit smart here. Between 0 and 2 pi, you're going to have two solutions. We're going from 0 to 51 pi. Now 51 pi is half a revolution more than a unit circle. So we're going to get 25, sorry, we're going to have 25 revolutions between 0 and 50 pi, but we're going to double that, so we're going to get 50 solutions. So you can sit there and count them up, or you can kind of think in terms of how many solutions there are in one revolution and just multiply that out to 50. So we've got 50 intersection points there. So how many solutions are there? You have got 50 solutions. Give a reason for your answer. You might even say that the minus 0.7 line intersects the sine graph 50 times over that domain. Any reason you give that is valid. All right. Question 7, an application of a trig function. A unicycle has got a wheel and tyre radius of 25 centimetres. It's moving at a constant speed. A dot starts at the maximum heights, and it's modelled against time. And we're given some information there. They've got a little graph down there to help you out as well too. So we are starting at the top of the wheel there, and we're doing one full revolution. All right, part A. We're given the circumference. We're told that the period is equal to circumference divided by speed. Show that the period is pi over 10. Okay, so we've got to show that the answer is going to be pi over 10. Now, there is our formula for period. We can say our period is going to be our circumference, because we've got circumference here, and circumference is 2 pi r. So it's going to be 2 times pi times our radius. And remember, our radius is given in the question. It's 25. So it's 2 pi r divided by our speed. And our speed is also given in the question, 500 centimetres per second. Now, it's always good just to check you're working in the same units as well. The radius is in centimetres, and the speed is in centimetres per second. So that means our period is going to be in seconds when we divide those. So on your, or you can even do this one in your head. So that's going to be 50 pi over 500, gives you your pi over 10. So the period for one rotation, pi over 10 seconds. Part B, hence, so again, there's that word hence. It means use what you have just done to help you with the next part. Hence, determine a model for the height of the dot above the ground. The cosine sketch below shows one rotation. All right, it's telling you that we have to use a cos function, and we know what the amplitude is. The amplitude is going to be the distance that's measured from the centre of oscillation of that graph. And the amplitude is just the radius of the tire. So our amplitude is actually going to be 25. So we can start writing down that h of t is going to be 25 times the cos of bt. So we've got bt plus c. Now c is your vertical translation. You have shifted your cos graph up 25 centimetres. So you've shifted your cos graph up 25 centimetres. The only thing we need to calculate now is b, which is our dilation factor, or our period. Now remember from your formula sheet, we know that the period, capital T, is equal to 2 pi divided by that b number. And we know that the period is pi over 10, because here's our period from before, it's pi over 10. So what we're trying to do is we're trying to solve pi over 10 equaling 2 pi over b. Now, you can solve that on your calculator if you need to, but basically we're going to get b equals 10. So b turns out to be 10. Sorry, not 10, 20. We're going to get b equals 20, I beg your pardon. So b should be 20, because 2 over 20 gives us our 10. So then we have our final function, ht. So the height is going to be 25 times the cos of 20t add on 25. So there is your mathematical model for the rotation or the height of the dot on that wheel. Now, let's graph that on the calculator, because we're going to need that to answer part C. So on the calculator, I'm just going to delete this graph. We are graphing, and it was 25 times cos of 20t, so 25 multiplied by the cos of 20x, so 25 times 20x, and then we're adding on 25. And if we go enter, there is our graph. It looks very messy because of the domain that we currently have, but let's tidy that up. So menu, window zoom, window settings. Now remember, we want to go from 0 up to a full period, and that full period was pi over 10. So we just need to go to pi over 10. And our y values, we're starting at 0. And remember, our maximum height was 50. We're going up as high as 50. There is our full graph for one period of that bicycle tyre. And if you have a look at that, it should match up with what's been drawn on your exam paper for you. Now, the second thing we need to do here is determine the time frame, so how long, when the height is bigger than 75 over 2 during the first rotation. So how high, determine the times for which the height is bigger than 75 over 2. We can put the 75 over 2 onto our graph that we've just drawn. So if we go tab, put in our 75 over 2, there is our line. And what we are trying to do is we are trying to find, I'm going to mark in the intersection point, so menu, analyze graph, intersection. We are trying to find those intersection points there and the other one as well. We're trying to find those intersection points, and I'm just going to move those out of the way a little bit. Okay. And I'm also going to shade them just so you can visually see. I'm going to go menu, analyze graph. I'm going to do a bounded area, and I'm going to go from there to there, and I'm going to do another bounded area, and I'm going to go from there up to the end. All right, don't worry too much about those numbers that are on there. All right, that shaded region that you can see, that is where the height of the bicycle tyre is bigger than 75/2. So we need to calculate what these times are. They're given in decimal form. It's going to be much nicer if we can solve an equation and figure that out in terms of pi. So on your calculator, add in a new page. I am going to solve my trig graph, which was 25 times the cos of 20t, whoops, got a 0 there, 20t, so 25 times cos of 20t, then it was add 25, and I want that to be equal to 75/2, and I'm going to solve it for the time, and I need to put in my domain, and my domain is 0 less than equal to t less than equal to pi on 10, because I'm only going up to pi on 10. And I have expression must be, what have I forgotten there? Solve that. Argument must be an expression. Solve 25 cos 20t for t. I've done something funny. Let's try that again. I didn't put a conditional command in there. That's right. So if I backspace that, that's got to be my conditional command. Given. That should be right. So solve that. Given that your domain is between 0 and pi on 10. That's better. We're getting pi on 60 and pi on 12. And those numbers there, pi divided by 60, is your 0.05, which matches up with your first x value there. And your pi on 12 is your 0.26, which matches up with your second x value there. So to answer your question, you would say that the height is above 75/2, in between 0 and pi on 60. Just check it was pi on 60. Yes, it was. So in between 0 and pi on 60, and between pi on 12 and pi on 10. So in terms of notation, 0 less than t less than pi on 60. So that was your first one. And the other time was pi on 12, I think it was. Yes, it was pi on 12. So pi on 12 less than the time less than pi on 10. So that would be your answer for part C. All right, question 8. You have got a cubic function and it does not have a stationary point. What is the value of the slope of the tangent at x equals 3? Show the equation has no stationary points. All right, let's get that function into the calculator. Okay, so we'll just wipe these pages here. And we're going to put in our cubic graph, which is x cubed minus 9x squared plus 28x take 28. There's our cubic. And straight away you can see from that, as the question said, there is no stationary point. So your cubic is coming up, it's flattening a little bit, but it doesn't go stationary, then it starts to take off again. And what we need to do is find the value of the slope of the tangent at x equals 3. So if I just zoom in there a little bit, let's put the point on the curve. So we're going to go Menu, Geometry, Points and Lines, point on. We're going to stick a point on this curve, and I'm going to stick it anywhere. It doesn't really matter because now I can change that coordinate. I've happened to stick it there. If I click the x value and change that to the number 3, hit enter, it defaults to 3,2, which is the y value is 2 on that curve. So x equals 3, y equals 2. The question said, find the value of the slope of the tangent at x equals 3. Now we can put a tangent on as well now. So menu, geometry, points and lines, tangent. And I'm going to put a tangent on the curve at that intersection point. Let's move that out of the way so we can see it. There is my tangent line, and it even gives me the equation of the tangent. And I can see by the coefficient of x, which is 1, that the gradient of that tangent is 1. And so straight away, part A, what is the value of the slope of the tangent at x equals 3? The tangent has a gradient of 1. If we wanted to use some calculus to do that instead, I'm going to add in a new page. I'm going to do the derivative. So I want the derivative with respect to x. Now I don't have to type my function in again. My function is f1. So I can just put in f1. I'm going to do the derivative of f1. I get 3x squared minus 18x plus 28. And now I want to substitute x equals 3 into that expression. So we want x equals 3. Quick way to do that, if I store that as the derivative, so control, store, and I'm just going to store that as d of x, d being derivative, and then I can get my d and substitute in my value of 3, and I'll get a gradient of 1. So I've done the derivative, I've stored it, I've substituted 3 into the derivative, and I get 1. And again, that matches up with the tangent that you've drawn as well. All right, the second part of that question, show that the equation has no stationary points. Now, visually, you can see that there's no stationary points, but we've got to demonstrate that using some algebra. Now, we've already done the derivative. Our derivative is sitting up here, and we've stored it. If we do completing the square on the derivative, so I'm going to go menu, algebra, completing the square, and I can type in d of x, or I can go up and just grab my derivative and paste it in. So if I do completing the square with respect to x, I get that. Now, you are trying to solve the derivative equaling 0 because you're proving that there are no stationary points. So you're effectively trying to solve, what was my result? It was 3x minus 3 squared. So 3x minus 3 squared plus 1. You want that to be equal to 0 because the derivative must equal 0 for stationary points. As soon as you try and solve that, you're going to get a negative number on the other side. And you're going to have to do the square root of a negative number at some stage. You cannot have the square root of a negative number, so there's no solution. All right, there is no solution. Hence, there are no stationary points on that curve. And again, if you try and solve that on the calculator, if you try and solve that function there, whoops, I need some brackets. If I try and solve that being equal to 0 for x, I just get false. There are no solutions. You can't solve it. Hence, there are no stationary points on that cubic curve. All right, that's question 8. I am out of time. We've only got 1 minute left, so I'm not going to start the next question. But you can download the TNS files from where you registered, and that will give you an indication of how to attack question 9 and 10. But the approaches there in 9 and 10 are fairly similar to what we've covered, so you should be able to follow those TNS files. So I'm going to stop it there. And if anyone has any questions, please post them up into the chat now and I'll do my best to answer them. If you don't have any questions, thank you for watching, and I hope